So remember, and what I want to do is motivate Le Chatelier a little bit more rather than thinking of heat as product. That seems sort of unsatisfying, if you think about it in terms of reaction equilibria. So let's think. Remember, if a reaction is exothermic, then raising temperature tends to shift it towards reactants. Backwards towards reactants, away from the products, because you think about it in terms of heat being a product. If a reaction is endothermic, then raising temperature shifts to products. It shifts it forward towards the products. Yeah, so we saw this before. An exothermic reaction, you decrease the temperature, and it goes and forms more of the product, right? So let's think of this in terms of free energies now. So if there is an equilibrium, we're assuming that we can reach equilibrium with this reaction, then we actually only have two choices, right? We can either have an exothermic reaction with an increase of entropy on the reaction, or we would have an endothermic reaction with a decrease in entropy. So one of these is spontaneous at high T, one is spontaneous at low T, but they're at equilibrium at some temperature. If you have an endothermic reaction with an exothermic reaction with an increase in entropy, it's always spontaneous. You're never really going to have reaction equilibrium because it always just fall forwards towards reactants. And if you have an endothermic reaction with a decrease in entropy, it's never spontaneous. It's always going to stay favoring the reactant. So generally, when we think about Le Chatelier, we think about reactions that do reach that have an observable equilibrium, that we can observe concentrations where there's moderate concentrations of everything on both sides at some temperature. And we're looking for changes in that. So what we have is a situation that either it's exothermic and the entropy is greater than zero, or sorry, it's endothermic and the entropy change is greater than zero, or it's exothermic and the entropy change is less than zero, that both of them have the same sign. Both the change in entropy and the change in enthalpy have the same sign. Okay, if that's the case, then if it's an exothermic reaction, then product increases with T. So if it's an endothermic reaction and equilibrium exists, then if it's endothermic, then the change in entropy has to be positive. We'll have a positive change in entropy. And delta G equals delta H minus T delta S. That means that positive delta S means that G is more negative a higher T, K becomes bigger and products increase. So really when we say, oh, it's an endothermic reaction, that's actually saying the same thing as it's a reaction with a positive change in entropy. If an exothermic reaction, then product decreases with temperature. Well, if it's an exothermic reaction and equilibrium exists, then it's exothermic, but also delta S is less than zero. It has the same sign. The entropy is decreasing in that reaction. So we have entropy. We have a decrease in entropy on reaction. And so looking at delta G equals delta H minus T delta S means that negative delta S means that delta G is more positive at higher T. K becomes smaller and the products decrease. So really, in Le Chatelier, if an equilibrium exists, if it's not something that's like almost entirely product or entirely reactant, then if there's a way to nudge the equilibrium and it's exothermic, that actually determines what the site of entropy is. So what Le Chatelier is really doing is it's actually looking at the entropy of the reaction, which we know, if the entropy is the temperature dependence on the spontaneity is really in the entropy, not the enthalpy. So it's a rather sneaky way that Le Chatelier can be thought of as, oh, heat is a product, heat is a reactant. It's really a backdoor to just thinking about what the entropy is doing. So if it's a reaction that increases the entropy, well, of course, a product is going to increase with temperature. If it's a reaction where the entropy decreases over the reaction, well, of course, the products are going to decrease over temperature. So that's an additional way to think about Le Chatelier's that is based more rigorously in the reaction constant rather than hand waving about products and reactants being heat. Okay, so that's the end of this segment.